You ever wonder what's really going on when someone says an AI model is learning? It's not some kind of magic, right? It's more like a mathematical quest, a search for the lowest possible point in this huge, complex landscape. So let's dive in and start the descent.
All right, so let's get right to it. How do AI models actually learn? I mean, what does that even mean? At its heart, learning is just about minimizing how wrong you are. The model makes a guess, it sees how wrong it was, and then it tries to make a slightly less wrong guess next time. The big question, though, is how does it know which direction is less wrong? Okay, I want you to picture this. Imagine a massive, totally fog-covered mountain range. We're going to call this the loss landscape. Now, every single point in this landscape, every peak, every valley, every little bump, represents one possible version of our AI model. And the altitude at that spot, that's how much error, or loss, that version of the model has. So what's the goal? Simple. Find the absolute lowest valley in the entire mountain range. The catch? You're basically blindfolded by all that fog. Now, you can probably guess that trying to map out that entire mountain range at once would take forever, right? It's just computationally way too expensive. So instead, we do something clever. We take little samples of our data, we call them batches. This is way faster, but it also has this cool side effect. It makes sure that the really difficult, tricky examples don't just get drowned out by the average. Each little batch gives us a slightly different, kind of fuzzy map of the landscape, which means our path down the mountain is going to be a little bit random, or as we call it, stochastic. So that brings us to our first, most basic strategy. Just go downhill. Sounds simple, right? But as you're about to see, the most obvious path is definitely not always the best one. And this method is called stochastic gradient descent, or SGD for short. It's kind of the granddaddy of all these optimizers. It's super straightforward. At every single step, it just looks at the ground right where it's standing, figures out which direction is the steepest way down, and takes one small step. That's it. Simple, right? Yeah, but it's got a pretty major weakness. And this slide just lays out the problem perfectly. The size of that step, what we call the learning rate, is absolutely everything. If your steps are too tiny, you're just going to crawl along and you could get stuck in the very first little ditch you come across, never making it to the real deep valley. But if your steps are too big, you just leap right over the target. You end up bouncing around erratically on the other side and never actually settle in. It's a total Goldilocks problem. You need it to be just right. So how do we get around this? Well, what if our little hiker had some weight to him? What if they could, build up some momentum? And that's the core idea behind momentum. Instead of just taking a single calculated step, we add a new concept, velocity. Think about it like a heavy bowling ball rolling down a hill. As it keeps moving in the same general direction, it picks up speed, right? And that extra oomph, that velocity, helps it roll right over the small bumps, those pesky little suboptimal valleys. And it also helps smooth out that jerky, zigzag path we were getting from using different data batches. So the key takeaway here is that updating our position is now a two-part thing. We're not just looking at the slope right underneath us anymore, we're also looking at the direction we were just going, our velocity, and we combine those two things together. This simple change makes our journey down that lost landscape way more stable, and usually a whole lot faster. Okay, but then there's this really clever little upgrade called Nesterov momentum. You see, classical momentum calculates the slope right where you are now. Nesterov is, it's smarter. It first takes a little look-ahead jump in the direction it's already going, and then it calculates the slope from that future point. It's literally like looking before you leap. It gives it a chance to make a smarter correction before it fully commits to the step. But look, momentum isn't the only way to solve this problem. There's a totally different approach. Instead of giving our hikers some weight, what if we could dynamically change the size of their steps, the learning rate itself, as they make their way down the mountain? This brings us to ADAGRAD, which stands for Adaptive Gradient. And the core idea here is honestly brilliant. It gives every single parameter inside the model its own personal learning rate. So parameters that have already changed a lot in the past get smaller updates, while the parameters that have barely moved get bigger ones. The whole point is to encourage progress across the board, on all fronts. But, and this is a big but, here's the fatal flaw. Because ADAGRAD is always adding up the history of changes, the learning rate for each parameter can only go down. It can never go back up. So eventually, it shrinks so much that the learning just grinds to a complete halt, even if the model is nowhere near its goal. It's basically a one-way street down to zero. And that's where RMS prop comes in to save the day. It fixes this exact problem. Instead of remembering the entire history of gradients, it uses a moving discounted average. So what does that mean? It just means it cares more about what's happened recently than what happened way back at the beginning. And that is the absolute key difference. The learning rate can now go back up if the situation calls for it, which stops it from stalling out way too early.
All right, so we've got one family of optimizers that's all about momentum and another that's all about adapting the learning rate. So what do you think would happen if we just smashed them together?
And that brings us to Adam. For a long time, Adam was the undisputed champion in most deep learning jobs. The name stands for adaptive moment estimation, and it does exactly what you'd think. It just takes the best of both worlds. Let's break that down real quick. From the momentum side of the family, it borrows that velocity idea to help smooth out the path and power through tricky spots. And from the RMS prop side, it borrows the whole adaptive learning rate concept, using that discounted average to tweak the step size for every parameter as it goes. And for a final little bit of polish, Adam also includes this clever bit of math called bias correction. All this really does is help make sure that the estimates it's using for velocity and step size are accurate right from the get-go. In the very early stages of training when it hasn't seen much of the landscape yet. So there you have it. Adam is the perfect optimizer. End of story, right? We just use it for everything and call it a day. Well, the reality, as it turns out, is a lot more surprising than that. So, is Adam always the best choice? The answer, pretty counterintuitively, is a big no. While Adam is for sure fast and super reliable, researchers started noticing something kind of strange about the final answers it was coming up with. It turns out that not all valleys are created equal. Adam is fantastic at finding these really sharp, narrow, steep valleys. The problem is, models that end up in those sharp valleys often don't generalize very well to new data they've never seen before. Think about it. A tiny little change in the input can send its errors skyrocketing up one of those steep walls. But the simpler, older method, good old SGD, it tends to find these wider, flatter basins. And models that settle down in those nice, flat minima, they're way more robust, and they tend to perform a lot better on new data. And this is really the main takeaway. The newest, fanciest, fastest algorithm isn't always the best one for the job. There's this fundamental trade-off between how fast you find a solution, which Adam is amazing at, and the quality of that final solution, which is where simple SGD often has this surprising counterintuitive edge. And what this all really demonstrates is that we are far from having this all figured out. This is still a super active area of research. People are coming up with new optimizers and new theories about why they work all the time. We are still very much in the process of mapping out this huge, complex landscape. So it leaves us with this really fascinating final thought, doesn't it? We're so often focused on speed and efficiency when we build AI, but if the absolute fastest path down the mountain doesn't actually lead to the best place to be, what other crucial trade-offs are we overlooking in our whole quest to build truly intelligent machines?